Hi and welcome back to Properties and Structure of Matter, and we're looking today at electron configuration. Now you will have been exposed to electron configuration again in the Stage 5 course, so we're going to build on that a little bit more today. So there's more information that is available on how we fill up our electron shells as opposed to what you learned in 7 to 10. So looking at our initial electron configuration, we were always talking about 2 electrons fitting inside that first shell, and that stays the same. Looking at our second shell, again 8 electrons can fill that shell. Previously we were looking at the third shell and that it could fit 8 electrons, whereas in actual fact it can fit 18, and we'll talk about why in a minute. And then we started filling up the fourth shell for our elements 19 and 20. But of course there are so many more elements than just elements 1 to 20, so those rules that you learnt were relevant to those first 20 elements. Working beyond there, however, there's a little bit more that we need to take into account. So how do I get these answers of 18 can fit in my third shell and so forth? Each shell can actually have a number of electrons, and we have a general formula that we use, which is 2n squared, where n is the shell number. So if we're looking here, our first shell, if we look 2n, so 2 times 1 squared, 1 squared is 1 times 2 is 2. So again, 2 times 2 squared, 2 squared is 4, 4 2s are 8. And so on. So we can see the third shell again, where n is 3, we will get 18, fourth shell 32, fifth shell is 50, and so on. So let's have a look. Now we would normally expect, using this information here, that potassium would have an electron configuration of 289, but it doesn't. And the reason is we are needing to build our atoms so that they are stable, and that requires us filling the fourth shell before, or start filling the fourth shell before we finish filling the third. So let's have a look at this. This is our little step that we use without any further information that will be coming in future videos, how we fill our periodic table. So if we have a look, the first thing we do, which is what we have done in the past, is we fill our first shell. Our first shell has a maximum number of electrons of 2. So we pop our 2 electrons in. In our second shell, there is a maximum there of 8 electrons, so we fill those 8. Now our third shell can fit 18 electrons. But because we're working on stability, and the reasons for this you will soon find out, because we're working on stability, we fill 8 electrons first. So 2 in the first, 8 in the second, 8 in the third. Before putting extras in that third shell, we have to pop 2 into our fourth shell. This works on stability, but it's also looking at energy, and the energy increases as we move up the number of shells. But there are some, when we talk about orbitals, some of those orbitals are lower in energy, so we have to fill those first. So we go up and we put 2 in that fourth shell. So that is for our elements potassium and calcium. Now for the next element that we go to fill up, we have to go back and fill up the rest of the third shell first. So then we go back and fill the remaining 10 electrons in there. Now we already have 2 electrons in our fourth shell, so we're going to put another 6 in there, where we're working again around 8. Then we're going to go back up and put 2 into our fifth shell, and then come back and fill that up. Now I know this is going to ask a whole lot of questions why, and those answers are coming. But at the moment, this is the procedure that we use to fill those electron shells. So Looking at this electron configuration, however, can provide us with a great deal of information about its chemical reactivity. So if we look at group 8 have completely filled electron shells and don't generally undergo chemical reactions. Now that's the electron configuration most elements are aiming for. So they then either gain or lose electrons to gain that ideal electron configuration of full shells. So we can see here group 8 completely filled shells. Group 1 have 1 electron in their outside shell, and you'll notice that all of them have 1 electron in their outside shell. So if we had filled potassium the way we thought we should, it wouldn't fill this pattern either. So they have similar chemical reactivity, and that's based on that 1 electron in the outside shell. So that provided a little bit of information for that. So they will be hoping to lose that 1 electron to gain that stable full shell. Group 7 has 7 electrons in their outside shell, and they all have 7 in their outside shell, all wanting to gain 1 electron to again get that noble gas configuration. So the only thing we can see here with regards to our periodic table is that hydrogen, while it is not a metal, it is not an alkali metal, it's positioned in that group 1, in that group 1 part of the periodic table. And the reason for that is it has 1 electron in its outside shell. So it, while very different to the alkali metals and it being a gas, there's 1 electron in that outside shell and it doesn't yet have that noble gas configuration, and it gets that by reacting with another element to give away 1 of its electrons, and that's why it's positioned where it currently is. So based on the information, based on the table that we had on an earlier slide, and I might pop that there for you, I want you to have a go at filling in the electron configurations for each of these elements. So argon is pretty straightforward, following the rules you always have done. Potassium and calcium, very similar. But have a go at iron, zinc and rubidium. The numbers of their electrons are there beside them. Follow the rules for the table on the right hand side and we'll check how you go in class. See you then.